In this example, I have a lawn roller, which if you've never seen one of these, they're very large, heavy, this one's exceptionally heavy, cylinders that we use to kind of flatten out bumpy grass. It can be really nice if you have a bumpy yard. In this case, I have a person who is pushing down on a massless handle with a force of 75 newtons at an angle of 40 degrees. The solid cylindrical lawn roller has a mass of 120 kilograms and a radius of 0.25 meters. And I know that the friction is sufficient so that the lawn roller rolls and it doesn't just slip and slide across. And I want to know, what is the acceleration of this lawn roller? And in this case, we can think about some of this force goes into accelerating the lawn roller in the horizontal direction. So we should be able to do some of the forces in the x direction is mass times acceleration in the x direction. But some of this force also goes into actually rolling this lawn roller because it rolls and it doesn't slip. And so we should also have some rotation that's happening. And in this case, I'm also going to use sum of the moments equals I alpha to try and figure that out. And perhaps even the best place to start is with a free body diagram. So let's draw a free body diagram of my lawn roller. I know I have a gravitational force. I know I have a normal force. I know I also have a frictional force. And then I finally have this, I'll call it pushing force, FP. And those are all the forces that are acting on my lawn roller. And here we should be able to go. So let's start here, because I know I want my acceleration in the x direction, and let's do it. So the two forces that are acting in the horizontal direction, I have a component of the pushing force, so I have Fp times cosine 40 degrees. And then I also have the frictional force, so minus the force of friction equals mass times acceleration in the x direction. I'm trying to find my acceleration in the x direction, and I know my mass and my pushing force, but I don't know my frictional force. And this is a case where I have static friction, so even if I knew the coefficient of static friction, I won't be able to solve for the frictional force explicitly because static friction, again, is less than or equal to the force that it can hold with the coefficient. So I'm going to have to leave this as a variable, and I don't know what this is. So I can't just use our old Newton's second law to completely solve this problem. And this is why I'm going to have to use the sum of the moments equals I alpha. And I now have to choose an axis about which I'm going to do the sum of the moments. There's two sort of reasonable choices here, but in this case, I'm going to go about the center. It's going to make my life a lot easier, so I'm going to go ahead and say sum of the moments about the center of mass, O. So sum of the moments about O, IO times alpha. And in this case, because I want about O, there's no moment caused by the normal force, there's no moment caused by gravity, and there's no moment caused by the pushing force. The only moment is caused by the force of friction. So the moments here will be the force of friction times the radius will equal my mass moment of inertia about the center times my angular acceleration. In this equation, I know my radius. I think I can calculate my mass moment of inertia because this is a solid cylinder and I know my mass and my radius. But I don't know my alpha. And this is another place where the actual x acceleration is related to the angular acceleration alpha. So first of all, let's go ahead and find my mass moment of inertia. For a solid cylinder, it's 1/2 mr squared. So my I, 1/2, 120 kilograms, 0.25 meters squared. This gives me a mass moment of inertia of 3.75 kilogram meters squared. And now relating my x direction acceleration and my alpha acceleration, I have to realize that these are coupled so that the bottom isn't moving. And for that to be true, as we talked about with our coupled motion, our acceleration and in the x direction will have to equal alpha times r. And in this case, we're going to need a negative sign in here. Is that true? this is, yeah, and that's because here, our force times our radius, this is going to give us a negative moment, which will give us a negative alpha, but we're moving in the positive x direction. So we want to make sure we keep all of those positives and negatives straight. So negative here, because our right-hand rule, we're going clockwise, this way, negative, so that should all work out. And now I think we have 3 equations and 3 unknowns, and we can solve for our AX. So let's plug everything in here. Our FP is 75 newtons times cosine 40 degrees minus our force of friction should equal 120 kilograms times our acceleration in the x direction. 2 unknowns there. Here, negative force of friction, we don't know. Radius 0.25 meters is our mass moment of inertia, 3.75 kilogram meters squared times alpha. That should give us an alpha in radians per second squared if our force is in newtons, or kilogram meters per second squared. And then our last equation, our acceleration in the x direction, will equal negative times our alpha times our radius, 2.5 meters. And solving these 3 equations gives us an acceleration in the x direction of this massive lawn roller of 0.319 kilograms. And if you're curious, it also gives us an angular acceleration alpha of negative 1.276 radians per second squared. Wow, I don't know why I said kilograms. This is meters per second squared. So, meters per second squared. And our force of friction in this case is 19.15 newtons. And that is our acceleration. So again, another example of coupling kind of linear Newton's second law and rotational Newton's second law using some of the coupled motion equations we've used earlier, mass moment of inertia, to solve a rotation problem.